Hello everyone, today I will be talking about exoplanets, how we can find them and how we can learn more about them. Now there are two main methods with which exoplanets can be found, apart from a few exceptions, and I will explain these two methods and then give a little outlook into the future with the James Webb Space Telescope and a research project at DLR Stuttgart. Now, the first method is the transit method, and quite interestingly, this method has found about 2/3 of all exoplanets found to this day, although statistically it is to be expected that this method only even can work for about 1% of all exoplanets that exist. So we know that there must be a lot more planets out there than we've found yet, and actually researchers have extrapolated from what we have found and how well we can find them, that probably about almost every star has one or more planets, and stars without a planet are really a rare exception. Now, the transit method works by observing a star's light and measuring how bright it is, and when a planet passes between its star and us, then it obviously dims the star's light as it covers a part of that star depending on how big the star is and how big the planet is, and you can measure those dips in intensity, and if they are very regular, very periodic, you can then conclude that there must be some sort of big object, probably a planet, orbiting that star and covering it from time to time. Now, of course, this only works if the orbital plane of that planet is so aligned with the line of sight between that star and us that it actually passes between us and that star. And since the distance between a planet and its star related to the size of that star usually varies by roughly 2 orders of magnitude. For example, the diameter of the Sun is roughly a little less than 1/100th of the distance between the Earth and the Sun. If we take that and our basic geometry, we can extrapolate that if other planets have a similar relation between distance and size of the star, then that means that about roughly 1 in 300 planets can even be found with this method at all, because the rest just orbits in a way that it never passes between us and its star. But this method is relatively easy compared to the radial velocity method. I'll compare what kind of precision instruments you'll need for both later. Now, the radial velocity method uses spectrometric measurements of that star, and it also depends on how the planet's orbital plane is aligned to us, but not as much, since you can theoretically detect any planet with this method. Just the closer aligned the orbital plane is to the line of sight between the star and us, the less precise measurements you need to find the planet. But it works unless it is actually exactly perpendicular to our line of sight, which is, of course, extremely unlikely. Now, the way it actually works is that since the planet has a mass, it will pull on its star, and actually for any two objects orbiting each other, the smaller object doesn't just orbit the center of the bigger object, they both orbit their common center of mass. This common center of mass just obviously happens to be a lot closer to the bigger object than to the smaller object, but the bigger object will also move, although a much smaller amount. So as the planet orbits the star also moves back and forth, or moves in a circle, which, if that plane is not perpendicular to us, will mean that it gets closer to us and then moves further away from us periodically from our point of view. And you can measure that using the Doppler effect, that is for any kind of wave that any object gives off, including light waves. If you move closer towards this object, then the waves essentially get squished between you, and if you move further away from the object, they get stretched out. You can imagine if you have something like a smooth surface and you give off these waves that then move towards the observer at the speed of light, then if you get closer and closer to the observer, the later waves that you give off have a shorter distance to travel and thus arrive relatively early, and so the time between these waves arriving is shorter than the time between these waves being given off. And so if a star moves towards us, then its light is a tiny little bit shifted towards blue as compared to the light it actually gives off. And if it moves away from us, the light we observe is a tiny little bit shifted towards red compared to the light it actually gives off. And a precise spectrometer measuring the spectrum of that star can actually measure this variation. If the star accelerates towards us or away from us periodically, you can see that spectrum shift back and forth periodically, especially since you can look for certain lines in that spectrum that are caused by certain chemical ingredients in that star. You can see these lines wiggle back and forth, which is of course much easier to measure than just a continuous spectrum moving. Now for a rough idea of what kind of precision you need for both these methods, if we look at the Sun and the Earth is roughly 1/100th of the Sun in diameter, so about 1/10,000th in surface area. So in order to measure the Earth with the transit method from a faraway star, you would need an instrument that can measure the brightness of the Sun to a precision of less than 1/10,000th, or with a much greater precision, since you want to actually see that transit out of the noise, so you need a precision of something greater than 1 in 30,000. Whereas with the radial velocity method, the Earth pulls on the Sun in a way that causes the Sun to move at speeds of about 10 centimeters a second, so about a 3 billionth of the speed of light. So the wavelength of the light of the Sun to an observer far away would shift by about 1/3 billionth, so you'd need a very precise spectrometer. Also, of course, you'd need a lot of data analysis, since the Earth's effect would overlap with the effects of other planets. And of course this would get easier to measure, or the signal gets bigger for planets that are either bigger than the Earth or closer to their star than the Earth. And also of course a smaller star also makes it easier to measure, since a smaller star causes for both methods the signal to be relatively big. A star that is smaller can be covered to a bigger percentage by the same planet for the transit method, and a star that is smaller also gets pulled around more by its planet for the radial velocity method. In fact, when the first exoplanets were found, there was a bit of unease, since we knew that our instruments have a limited capability, and that we will probably discover more exoplanets and other exoplanets as our instruments get better. But obviously when the first exoplanets were discovered, most of these planets were huge gas giants orbiting very small stars at a very small distance. So there was actually the hypothesis for a while that maybe these are just the most common planets and small rocky planets like the Earth are more of an exception. Now we know that small rocky planets like the Earth also are quite common, and that this shift was just because the earliest instruments were just that precise, and big gas giants orbiting a small star very closely are just the easiest exoplanets to find. So of course most of the first exoplanets we found were this kind of planet. Now there are two future projects that might make it easier to find exoplanets. There are of course a lot more, but these two are the ones that I'd like to talk about. One is the project for hunting exoplanets at DLR Stuttgart, where they use a special laser. That laser was earlier built in a physics project, and the way this laser basically self-adjusts is very complicated from a physics standpoint, and I'm not going to go in depth about it, but this laser gives off a set spectral line or a set frequency of light with an absolutely unbelievable precision. And they can use that as a kind of ruler. Most optical instruments, most astronomical instruments, most spectrometers tend to be a little bit imprecise. They shift. If the temperature changes, they get different results. If there's any vibration, they get different results. So there's a limit to how precise they can measure the spectrum of a star. And what they do is they let this laser produce very precise spectral lines, and they then mirror a tiny bit of this laser's light into the spectrometer, and it doesn't really mess with the measurements they're making because it's only very specific spectral lines, but they can use it like a ruler to calibrate the spectrometer by and recalibrate the spectrometer by, as they know exactly what wavelength this light is, and they can then see that line in the measurement, adjust the measurement so that this line fits the wavelength they know the laser gives off, and thereby adjust the rest of the measurement, so they can make spectrometric measurements to a extreme precision, and thus this might help find exoplanets using the radial velocity method with a lot more precision, finding smaller planets and getting more precise information about these planets. Now currently there are very limited ways we can learn more about exoplanets. We can measure its size since we know the star's size, and with the transit method we can measure how much percentage of the star's light is blocked out, or how many hundred thousands of the star's light are blocked out, and thus we can then know how big the planet must be. And of course with both methods we can quite easily measure the orbital period of the planet, since with the transit method we can just measure how often the light dims, and with the radial velocity method we can measure how fast the period of the star moving back and forth is. And if we know the orbital period and we know the mass of the star, then we can also tell how far away from the star the planet must be. And then by measuring how strong the star moves back and forth in the radial velocity method, we can also measure how heavy the planet must be. There is also a chance to learn more about a planet by measuring spectral lines and spectrometry, as a part of the light we get from a star with an exoplanet is reflected light from that exoplanet that has passed over the exoplanet's surface, and if the planet has an atmosphere, through the exoplanet's atmosphere, and so we can find the spectral lines of chemical compounds in that atmosphere in the spectrum of the star as absorption lines, as weak absorption lines, of course, since only a small part of the light is actually reflected light of the planet. And that's actually a problem because you need a really precise spectrometer to actually precisely measure those absorption lines, and here the James Webb Space Telescope might help. Now, the James Webb Space Telescope, among other research projects, will also help searching for exoplanets, and the really cool part about that is that it has such a precision and such a resolution that it might actually be able to see certain exoplanets separate from its star. Now, both the star and the exoplanet will still be smaller than 1 pixel, but the distance between the star and the exoplanet will be more than 1 pixel, so you'll be able to see the star and the exoplanet separately, thus be able to learn a lot more about its characteristics, and you also get light from the exoplanet clearly separated from the star's original light, so you can make much easier spectrographic measurements of the light reflected by the exoplanet, and learn a lot more about the chemical compounds in its atmosphere if it has one, which might help us search for life, as there are certain chemical compounds you only find in an atmosphere if there's life, or, well, the exact definition of life is still a matter of biology and philosophy and basically semantics, but some sort of life-like system must be there if there are certain chemical compounds together in the atmosphere, since without any active source producing these compounds, they would deteriorate into each other. So if you find certain chemical compounds to both exist in an atmosphere at the same time over a longer period, you know that something must essentially be breathing there. It might just be microbes, most likely, but there must be some sort of proto-life. And actually, if you look at the precision the James Webb Space Telescope will probably reach, then you could separate the Sun and the Earth as two separate little bright dots from several hundred light years away, so there are a lot of stars which, if they have planets, we can see the planets and the stars as two separate pixels and thus make very precise measurements of the planet's optical spectrum. Now, I hope this was kind of interesting. I might talk further about astronomy and exoplanets if you are interested in that. I'm always open for questions or suggestions, and as always, thanks for watching.